Every interaction in classical electromagnetics begins with a simple configuration, a positive and a negative charge situated in empty space. To map the system's influence at a specific coordinate, we calculate the electric field vector. At this arbitrary point B, the positive charge generates a field of 3.6 times 10 to the fourth newtons per coulomb, pointing directly to the left. Simultaneously, the negative charge pulls to the right, with a magnitude of 4 times 10 to the third newtons per coulomb. Subtracting the weaker pull from the stronger gives us the net magnitude and direction of the electric field at point B, 3.2 times 10 to the fourth, directed left. Shifting our focus to an equidistant point C requires more complex math. Here, both charges generate distinct vectors with identical magnitudes of 9 times 10 to the third newtons per coulomb, but they act at diverging angles. We resolve this through trigonometric superposition. By summing their cosines, we yield a single resultant vector pointing perfectly to the right. If we attempt to map the entire field by extrapolating this process across millions of coordinates, the visual clarity collapses. The screen becomes a chaotic mass of overlapping arrows. This point-by-point calculation provides mathematical results for specific locations, but it leaves us structurally blind to the global shape of the electric field. Faraday looked to map these forces visually rather than purely algebraically. He wanted to see the field as a whole, not as isolated data points. Faraday initially used the term lines of force. However, this is somewhat misleading, particularly in magnetic fields, where the actual force acts perpendicularly to the pattern seen here. We now use the term field lines. These lines are often treated as simple drawing aids, qualitative sketches used to illustrate a general concept. But the formal definition is rigorous. A field line is a curve in space where the tangent at any point specifies the exact direction of the net electric field at that location. This leads to our central thesis. Field lines function as a geometric framework where spatial density directly reflects the inverse square decay of electric field strength. The primary difficulty in mapping this decay is a conflict of dimensions. We draw these figures on flat, two-dimensional surfaces. In reality, electric charges exist in three-dimensional space, radiating their fields spherically in every direction. Because of this, we cannot accurately measure field strength simply by looking at the distance between two lines on a piece of paper. To evaluate the density of a 3D field, we must track the number of lines crossing a unit cross-sectional area that is held perpendicular to the lines themselves. Projecting a three-dimensional field onto a two-dimensional plane breaks this quantitative measurement. We need a specific geometric tool to bridge these dimensions. Consider how we define a standard angle in 2 dimensions. If we place a line element, delta L, at a distance r from an origin, the angle it subtends is delta L divided by the radius. To bring this into the 3rd dimension, we rotate this geometry, expanding the line into a surface and the angle into a cone. This 3-dimensional vertex is called the solid angle, represented by the symbol delta omega. The formula for a solid angle is the perpendicular plane area, delta S, divided by the square of the distance, r squared. Within this geometry, a fundamental rule applies. The absolute number of radial field lines inside a given solid angle remains constant, regardless of the distance from the source. The solid angle is the bridge we need. It allows us to track how a constant number of lines is distributed as the surrounding space expands. We can now finalize the proof. We cast a fixed number of radial field lines, n, through our solid angle cone. We intersect the cone with 2 area elements, one at distance r1 and a second, larger area further out at distance r2. By rearranging our formula, we see that the area of these elements grows by the square of the distance. The first area is r1 squared times delta omega. The second is r2 squared times delta omega. To find the field density at each point, we divide our constant number of lines by these areas. This gives us n over r1 squared delta omega at the first point and n over r2 squared delta omega at the second. Because n and the solid angle are constants, the visual density of these lines mathematically mirrors the 1 over r squared decay of the electric field. The geometry and the physics are perfectly aligned. Applying these rules of density transforms an isolated positive charge into a perfectly uniform sunburst, where the lines radiate and thin out according to the inverse square law. In a dipole configuration with opposite charges, field lines form continuous curves, densely packed to map mutual attraction. But with two identical positive charges, the topology shifts. The lines warp away from one another, leaving a void where the net field is zero. These curves provide a precise, readable map of forces across an entire system. Because field lines represent real physical laws, they follow four absolute constraints. They must start on positive charges and end on negative charges, and they must remain continuous in a vacuum. Third, two field lines can never cross each other. An intersection would mean that a single point in space has a net field pointing in two different directions at the same time, a mathematical absurdity. Finally, electrostatic field lines never form closed loops. This is a direct result of the conservative nature of the field. You cannot follow a path through a static electric field and end up back where you started with a change in potential. Faraday's field lines are more than a visualization tool. They are a profound geometric translation of the calculus of space, allowing us to see the invisible mechanics